Have you ever wondered how a pathologist can look at a piece of tissue days, weeks, or even years after it was removed from a body? Well, today we're diving into tissue fixation. It's this incredible, almost invisible art of stopping time at a cellular level. And trust me, getting this one step right is the absolute foundation of modern medicine and diagnosis. Welcome to FZ-LabTech. Let's get right into this fascinating process. Okay, picture this. The moment a tissue sample, a biopsy, is taken from a patient, a silent crisis begins. It's this frantic race against the clock, and believe me, the stakes could not be higher. So, what is this crisis I'm talking about? Well, the second a piece of tissue is removed from its blood supply, it starts a process of self-destruction. And if we don't step in and stop it, getting an accurate diagnosis becomes impossible. This process is called autolysis, and what that means is the cell's own digestive enzymes get released and just start breaking everything down from the inside out. It's kind of like a microscopic meltdown, and our number one job is to stop it in its tracks and fast. And that is where our hero of the day comes in: fixation. This is the essential step, the process that just slams on the brakes and halts that cellular self-destruction dead in its tracks. Honestly, the best way to think about fixation is like a form of biological photography. The whole goal is to capture a perfect, super high-resolution snapshot of the tissue exactly as it was inside the body. We're essentially freezing a fleeting moment in time so we can actually study it in detail. So, what makes for a good snapshot? Well, first, we've got to stop that autolysis to preserve the tissue. Doing that also maintains the cell's original shape, we call that its morphology, and it stops all the important bits and pieces from just washing away. Fixation also firms up the tissue, which is super important so we can actually handle it. And crucially, it enhances its ability to take up stain, which is what lets us see all those incredible details under a microscope. Okay, so to get all this done, lab techs have a whole toolkit of different methods and mechanisms. And it is definitely not a one-size-fits-all kind of deal. You have to pick the right tool for the job. So you can basically break these methods down into two big categories: chemical and physical. By far the most common is chemical immersion. I mean, you literally just drop the tissue into a jar of fixative. But of course, there are more specialized techniques, right? Like perfusion, which is mostly for research. And then you have the physical methods. You can use microwaves to really speed things up, or something called cryofixation, which is just super fast freezing to instantly lock everything in place. All right, so digging a little deeper into the chemical side of things, there are two main ways these fixatives work. You've got your coagulant fixatives, like alcohol. Think of these as scrambling things up. They cause the proteins to tangle together, creating this mesh that traps everything. Then you have the non-coagulants, like formaldehyde. These are way more precise. They act more like a scaffold, creating chemical links between proteins to build a really stable gel. Okay, so this brings us to the real all-stars of the fixation world. Let's meet the chemicals that are doing all the heavy lifting in labs day in and day out. And look, if there is one number you remember from all of this for routine histology, let it be this one: 10%. We're talking about 10% neutral buffered formalin, the absolute, undisputed king of fixatives. Formalin is just the ultimate workhorse. As a non-coagulant, it forms these really nice, stable crosslinks that give us great structural detail for most routine work. Plus, it's cheap and it's effective. So what's the catch? Well, its main drawback is speed. It only penetrates tissue at about 1 millimeter per hour. And that right there is absolutely critical. It means you have to give it enough time to work its way through the entire sample. A big specimen that's left for too short a time can end up perfectly fixed on the outside, but be a completely broken down mess on the inside. And you just can't make a diagnosis from that. But okay, what if you need to see things in even more detail? What if you need to look inside the cell, at the organelles themselves? Well, for that, you're going to need a specialist. You need glutaraldehyde. Yeah, if formalin is your trusty all-purpose camera lens that you use for pretty much everything, then glutaraldehyde is that super powerful macro lens you pull out for the extreme close-ups. It is the absolute go-to for electron microscopy. Why? Because its crosslinks are rapid and irreversible, preserving the finest, tiniest details inside a cell, what we call the ultrastructure. The trade-off, though, is its terrible penetration, which means you can only use it on really, really small tissue samples. So, look, knowing which fixative to grab off the shelf is one thing, but using it correctly, that is everything. Let's go over the golden rules that will guarantee a perfect artifact-free fixation every single time. And these are absolutely non-negotiable. First up, thickness.
The tissue has to be thin enough. We're talking 2 to 4 millimeters so the fixative can get all the way through, which leads directly to time. You need to give it enough time to work, usually somewhere between 6 and 24 hours. Temperature is pretty standard. Just room temp is fine for most routine stuff. And finally, volume. This one is huge. You need at least 10 times the volume of fixative to the volume of tissue. If you don't, the fixative just gets diluted and won't work properly. And you know what happens when those rules get broken? You get artifacts. These are like flaws or glitches in our photograph that can totally obscure a diagnosis. For example, if you use unbuffered acidic formalin, you get this ugly brownish-black stuff called formalin pigment. If you don't fix it completely, you get fuzzy, blurry staining where you can't see anything clearly. And if you leave it in for way too long, the tissue can actually shrink and get all distorted. A good lab knows not just how to spot these, but more importantly, how to prevent them from happening in the first place. All right. Wow, we've covered a lot of ground here. Let's pull all of this together into one simple, quick reference cheat sheet for you.
Okay, here it is. Your at-a-glance guide to the big players. You've got our workhorse, 10% NBF for all your routine histology. The specialist, glutaraldehyde, for when you're going deep with electron microscopy. Then you have the alcohols, your coagulants, which are great for cytology and for preserving things like nucleic acids. And last but not least, the highly toxic but totally essential osmium tetroxide. It's used as a second fixative in EM to really make lipids and membranes pop. This is pretty much your core toolkit. And I really want to leave you with this one thought because it is a fundamental truth in literally every histology lab on the planet. Every single step that comes after fixation, the processing, embedding, sectioning, staining, it all depends completely on how good that initial fixation was. You just can't fix a bad fix. It is without a doubt the cornerstone of every single diagnosis. And that's our deep dive into fixation. If you found this helpful and you want more lab concepts broken down just like this, make sure you subscribe to FZ-LabTech. Thanks so much for watching.